I'd like to spend this week talking about curves and surfaces. Many computer graphics courses, the topic isn't covered, but I like to cover it for a couple of reasons. One is that if you go along the way we've been going, you think the world is composed of little polygons or lots and lots of triangles. And although our hardware has to render things as line segments or triangles, if you're dealing with an application, you want to work at a higher level. So we can think of this as an extension of some of the ideas we've had the last few weeks about modeling. So now we're going to build a model with curves if it's one-dimensional kinds of entities, and more. I really want to get into surfaces, but we'll get surfaces out of learning about curves. Now, ultimately, as we'll see at the end of this set of lectures, that we're going to wind up rendering the curves and surfaces as a lot of little line segments for curves and a lot of triangles for surfaces, and we'll see how we do that. But in terms of building the model, we can describe many surfaces as very nice kinds of polygonal, parametric polygonal curves and surfaces, and that's what we really would like to get at, is what the modeler sees, and then understand that underneath the model is going to be a layer that converts that to the kinds of entities that we can handle with the graphics system. So what we're going to do in this lecture is look at the different representations we could have of curves and surfaces. We've talked about them briefly before. There's the explicit, the implicit, and the parametric forms, and each of them has its own strengths and weaknesses. We're going to really wind up talking almost exclusively about parametric polynomial curves and surfaces, although quadrics will be a special case where we'll see we can deal with those in other ways. And each of those has its own good points and bad points, and that's kind of what we want to discuss in this lecture is see what kind of conditions do we need to specify a particular curve or surface, and when we start moving around the data that determines those curves and surfaces, we want to have some element of stability. That basic definition is if you change some parameter a little bit, you move one of the points that determines the curve or surface a little bit, you shouldn't see a very large change in the resulting curve or surface. So that's what we're going to be doing. This is sort of pointing out more what we just said, is that we really want to work with curves and surfaces at a higher level and see how they fit with the graphics hardware, or more in particular, how they fit with kind of OpenGL view of the world. So let's start with the following. Let's say, okay, suppose I give you a bunch of points. And one of the things that we're going to see is that if we're talking about CAD modeling, the sort of standard way you model some kind of a surface is to give you certain points that may be on the surface. It's same is true of curves. Everything I say with curves and surfaces is going to be true of each other. We'll go back and forth. So we may say, okay, here's some data points, and they must be on that curve or surface. They're called interpolating data points, because the whatever curve or surface I derive from them has to pass exactly through that. But more likely what happens in realistic applications is you just want to be close. You don't have to interpolate exactly. And the reason for that is that you give up a lot by saying that you have to interpolate through those points. In general, what you wind up is giving up a lot of smoothness, and smoothness is certainly something we want in our modeling applications. So if you look at the various representations, then let's keep in mind the following points. First, stability is an issue. That was the issue. If we change any input data a little bit, we want the resulting curve or surface to only change a little bit. We want smoothness. You can pass, if you wind up passing data through a bunch of points, but the resulting surface has a lot of jaggedness to it in order to force it to pass through, that's not a particularly useful surface. I mean, if you think about examples like trying to model car shapes, which is one of the original sources of the kinds of curves and surfaces we're going to be talking about. Is you don't want something that meets at a very sharp angle, because you want to mold the metal or the plastic or the fiberglass to have this nice shape. If it's going to be in some sort of graphical application or coupled to graphics to render that, you want these curves and surfaces to be easy to evaluate. You don't want something that's mathematically very nice and very elegant and has this mathematical representation in some sort of equation. But if you can't solve that equation at all, or you can't solve it without an awful lot of work, then it's not necessarily going to be a useful representation of that curve or surface. So we want easy to evaluate curves and surfaces, hopefully so that we can do real-time applications with them. Okay, and as we said in the previous slide, in a given situation, do we have to interpolate data, or can we just come close? Often we have a mixture of the two. Certain data points have to be interpolated, and some we can just come close to. Then the final issue it has to do with derivatives. Derivatives are, if you look at the resulting curve or surface, its derivative can be a very good measure of its smoothness. If a curve is continuous, the derivative may not be. The second derivative may not be. And those are, as we've said, important points for getting a useful representation or a useful curve and surface. But the other way to look at this derivative issue is not only do we measure smoothness in terms of derivatives, but when we derive the curve or surface, do I need derivative information? That's going to be a crucial difference between what we do with CAD and graphics and what you might be doing in some numerical methods course where you're talking about curves and surfaces. So let's go back now and start with the three different representations of curves and surfaces that we talked a little bit about it before, but let's go through that quickly. So the simplest form is, and let's start with a 2D curve, is to just say, well, I have a function that I know explicitly. I really know what that function is. It could be a polynomial, it could have trigonometric functions or something, but if I give you an x, I know how to evaluate that function and give you the corresponding y. Now, one of the problems with that is that it says that there's exactly one y for each x, which is certainly not true for all curves and surfaces, and especially many curves and surfaces of interest. So the simplest example is if you take a line, you can't represent a vertical line that way because it has a representation x is constant, but that you can't write it in the form y equals a function of x. If you take a very simple thing like a circle, nice smooth curve, the best you can do is write something like y is the square root of r squared minus x squared if it's a circle centered at the origin. But that only gives you one of the two values. You also have the value that y equals minus the square root of r squared minus x squared. So that's not a representation because it's giving you two values for every x. Now, if you go to 3D, the corresponding forms are really twofold. If you want a curve in 3 dimensions, explicitly, then you have two functions. One that determines the y for every x and another that determines the z for every x. If you want to talk about a surface, then a surface is a function of two variables, and so you could say that that all of the z's are given as some explicit function of x and y. And again, you have the same issue that not all surfaces and not all curves in 3 dimensions can be represented explicitly. So it's a nice form if it works, but it turns out of all the forms, it's the least useful in CAD and computer graphics. Now the next form is the implicit representation, where in 2 dimensions you have a function that you can evaluate of x and y, and wherever it's 0, that says you're on the curve. Now sometimes that's called a membership function because it divides space up into 2 regions, one for which the value is 0 and then all the rest of it where the value of g is not equal to 0. Now the problem with that, because if you think of it as a membership function, is that it doesn't tell you how to get an x for any y or a y for any x. There may be no corresponding explicit form, and so it's really kind of a testing function. If I give you an x and a y, I can tell you whether you're on the curve or not. But you're used to that, because if you take something like a circle, then we're used to saying every circle centered at the origin can be written as x squared plus y squared minus r squared equals 0. You can also write any line of the form in the form ax plus by plus c equals 0 for proper choices of a, b, and c, and that'll include both vertical and horizontal lines. So you sort of, in general, what happens is that the implicit representation is more robust, and you can represent more curves and surfaces using the implicit form, but again, you can't solve it. If you go to 3 dimensions, then the function g of x, y, z equals 0 defines a surface. So for example, a sphere centered at the origin is x squared plus y squared plus z squared minus r squared equals 0. And if you're dealing with implicit representations in 3 dimensions, then you get curves by looking at the intersection between 2 surfaces. But the difficulty, again, is that you can't solve it in general. It turns out if you're doing things like ray tracing, you can often use an implicit representation in conjunction with another representation to trace rays, and we'll see a little bit of that the last week of the class. Also, if you're dealing with quadrics, things like ellipsoids and hyperboloids and paraboloids, this kind of form actually does work for that limited case. Okay, now the most robust, well, here's the case for quadric forms. Here's algebraic surfaces are those for which every term in the function g of x, y, z is a polynomial in x, y, and z, and you can, if it's quadric where the sum of the 3 powers is less than or equal to 2. So if you count out all the possibilities you have, including power 0, so you can get constant and linear terms, there's most 10 terms, and we'll look at that representation a little bit later. And as I mentioned in the last slide, it works with ray tracing. You can actually do it because it'll reduce everything to the quadratic equation, and we know we can solve the quadratic equation explicitly. Okay, we'll come back to that. Okay, now parametric is the one we're going to be spending the next few lectures on. It says that we have a parameter for a curve, u, and as u goes over some range, we have explicit functions x of u, y of u, and z of u that gives us a point in space. So we can say a point in space P is given for a given value of u by x of u, y of u, z of u. It turns out if you're working with homogeneous coordinates, we'll at times want to put in a w of u, and we'll see that in a lecture or two, just when we talk about NURBS, curves, and surfaces, where you can actually have the w value also defined by a parametric equation, and you'll go back to xyz space by just dividing doing a perspective division by dividing by w. Okay, so as you trace out, so this is, and any of you have had calculus 3 have probably seen this if you talk about vector analysis, that as you trace out a curve for values of u going over some range, actually, if you evaluate p of u over some range, it defines a curve in space. And one of the things that I probably should have mentioned earlier is that one of the nice things about parametric form and it being more robust is it doesn't really depend on a particular coordinate system. You get x, y, and z out of this, but the problem often with explicit and implicit forms is they depend on having an underlying coordinate system. And for example, with lines, if you write y equals ax plus b, it'll work, but not for vertical lines. But that depends on what axes you pick for the x and y dimension. This kind of representation, as if you've studied vector analysis is much more robust and doesn't depend as much on the underlying coordinate system or frame. Okay, so let's just focus on this one a little bit. Okay, so what is a good function for these parametric lines? Well, if we go back to what we said a few slides ago, we want functions which we can evaluate easily. We also want functions that we can determine fairly easily from given data. So if you say, well, I want you to interpolate these points, what kind of functions would you choose to do that? It'll turn out to be polynomial functions. And we also, because in graphics, we want to use normals for shading and lighting, and also just to have smoothness that we can actually measure and control. We want to be able to compute derivatives, or in 3 dimensions, we want to be able to talk about the normal to the surface at every point. So that's going to determine what kind of functions we have. And in general, we want functions which are very smooth as we change u, or in 3-dimensional surfaces, we'll have 2 parameters, u and v. So some of the ones we've already seen are the line, a parametric line going between 2 given points, p0 and p1, looks like p of u is 1 minus u times p0, where if u is 0, you get p0 plus u p1, and if u is 1, you get p1. So that's the, as we saw, was the convex combination of p0 and p1. If you extend that out to values of u bigger than 1, you go out here, and less than 1, less than 0, you go out in this direction. So really, this describes an infinitely long line if you allow u to vary over a larger range. If you do it using a vector d to points in this direction, then you can write it alternately as p0 plus u times d, and if u is positive, it goes out this way. That's called array, because as u goes from 0 to infinity, you get all of the points on the semi-infinite line. It's infinite in one direction, but doesn't go in the other direction. So we've seen that one. If we want to now move to surfaces, we have a function of 2 variables. It's u and v, and we have explicit parametric forms for x, y, and z. So any point on the surface is determined by x of u and v, y of u. So u and v and z of u and v. So often the way we do this is, well, if I look at a u and v plane, so here's u and here v, it sort of says as you look at this rectangle in u and v, I can pick any point and then go back up and get a value of z here. Okay, but let's look at it just slightly different way. That's not particularly good. Let's look at it this way. What I want to argue is that if you know about curves, you know about surfaces. Because if I set u equal to 0, then I have a parametric curve in v, and it might look like this edge. If I set u equal to 1, I get a parametric curve in this direction. Okay. Likewise, if I set v equal to 0, I have a parametric curve in u, and if I set v equal to 1, I get this parametric curve here. They obviously have to agree at the corners, because you have 0, 0, 0, 1, 1, 0, and 1, 1 at the corners. And in fact, if you look at it this way, suppose I look at this curve p of u 0 here, and now I change the 0 to be small amount, 0.01 say. I now have a parametric curve which is a little bit different from p of u and 0, but if I look at that sort of continuously, as I make little bitty changes, I trace out a surface. So I think it's pretty straightforward to convince yourself that if you know about curves, you kind of know about surfaces, because all you're doing is sort of connecting all of these curves as I change either u or v a little bit. So you want the same kind of properties, because if we build our surfaces from curves in either u or v, I want smoothness, I want to be able to evaluate derivatives and normals, and I care about how easy it is to evaluate these functions x, y, and z. Okay. Now, I also said that I want to be able, in order to do shading calculations, lighting calculations at any point, I need the normal. And if you have a parametric representation, then you can always get the normal from the derivatives, the partial derivatives of the x, y, and z functions. And I can take the partial derivative with respect to u and the partial derivative with respect to v. We saw this when we were talking about bump mapping. It turns out that these two vectors lie in the tangent plane at that point, and if I take their cross product, I get something that's orthogonal to both of them, which has to be the normal coming out of the tangent plane at that point. So, the point here is that if you use a simple representation for x, y, and z, then it's fairly easy to get the normals by taking these derivatives. And it's another reason that we're going to wind up using parametric polynomials or polynomials in both u and v, because I can differentiate those fairly easily. Okay, sort of a special case is the plane. It's much simpler, and generally we'll write it in one of two forms. If we use the idea that the normal, that you need one point and this normal to the plane, or let's suppose you have two vectors that come out of this point, I can take their cross product to get the normal, and then I get this kind of a representation that p0 is a point on it, plus u times the first vector plus v times the second. If you go back to when we first introduced ways of dealing with geometry, we said that a point plus a vector is a point, and a point plus a vector must be a point, and a scalar times a vector is a vector. So all of this is consistent with everything that we've done before. So here's the surface. If you use the 3-point form and say every 3 points determines a triangle which is flat, and also the plane that triangle lies into, then you can say, well, Q is just P2 minus P0, and R is just P1 minus P0, and so you get the 3-point form of the plane. That also is the way that we've seen to get triangles. The other one that's important, again, one we've seen a little bit, is a sphere. Just to again give you another example of parametric form, where I'm using, instead of u and v, I'm using theta and phi, because generally they're the angles when you talk about longitude and latitude. So here's another parametric form for x, y, and z. We'll come back, probably see this a couple of times, because we'll talk about issues like the distortion at the poles. But here's again a reminder that for the unit sphere, the normal is just given by the point. You can show that. I think we did this before by just differentiating this with u and with respect to the theta and phi, and then take the cross product, and you'll see it comes out to just be, when you normalize it, to just be the value of the point. Okay, now one of the things that's going to distinguish what we do in CAD applications and graphics from what you might have studied. I know if you're computer science majors and took 375, you probably did a little bit of this in numerical methods. That what you tend to do when you're studying numerical analysis is you look at sort of a general form of a curve where you have lots and lots of data points. So you talk about things like the interpolating polynomial for any number of points. The problem is it's not particularly a useful way in computer graphics. In computer graphics and CAD, what you generally want to do is take a small number of points and evaluate a curve over a short distance that's determined by those data points. Reasons being that it gives you a more stable representation. It also gives you something that's generally very fast to evaluate. So we would take some data and we would try and get a short curve over some range of u. And then what I do is I take some other data and I get another curve that's valid over a different range of u. And now I have a slight complication here, which is that if I have these two parametric curves and I want to have any degree of smoothness, then they have to be continuous at this point. So I generate, if u goes over 0 to 1 for the red curve, and then starts again at 0 for the blue curve, then I want to make sure that q of 0 is the same as p of 1 to get this continuity. So I have a sort of an additional condition I get by saying I want to work in segments. But we're virtually always going to want to work in segments. It's sort of the natural way. Now the extension of that to dealing with surfaces is, rather than deal with a whole large surface, you deal with small pieces of surfaces that are called surface patches. And then the patches have to have some continuity where two different patches meet, and we'll see that as we go along. Okay, so now that's one idea, that we're going to work with small segments or small patches. The second idea goes back to this issue of evaluation, that I want to be able to evaluate things easily. So that the idea here is that I want to have parametric forms for my curves and surfaces. So I say, well, okay, for a curve, then I'm going to say that x of u, y of u, and z of u can each be given by a different polynomial representation, and the polynomials may have a different degree. But they're of the form c0 plus c0 plus c1u plus c2u squared, and the constant c's could be different for the x, y's, and z's, and generally will. So if you look at and what we'll almost always want to do is have n, m, and l always be the same. Here I call it k, but to say what I mean, one of these has to be changed. So if they're generally, we're going to look at cubics. So n is going to be 3. So I have 4 coefficients for each one, and what I would then have to do is determine 12 coefficients. But what we can observe is, look, these are all independent of each other. So what I really have is 3 sets of n plus 1 coefficients, and so for cubics, I would have 3 independent sets of equations that determine 4 coefficients for each one, and we'll see how we do that for various conditions. So what's going to make them different and give you different values of the c's is what kind of conditions we want to impose. Okay. So just review why polynomials. Well, as we said, they're easy to evaluate, but they also have the property that a polynomial is continuous everywhere. It doesn't all of a sudden take a jump, and any polynomial can always be differentiated. I mean, that's calculus 1. You take a polynomial and you differentiate it, you get a polynomial of 1 degree 1 less. So you don't have to worry about too much about what's going on here in the middle. You just have to worry about what goes on here at the join point. So as we saw in a couple of slides ago, that you want continuity here, but you also want to say, wait a minute, they're continuous here, but this is a lousy curve to determine the shape of anything because the derivative is discontinuous. So, but for a polynomial, because you can evaluate it, you could say exactly what you need to make this derivative continuous here, and likewise for any derivative, the second derivative, third derivative, so on. Now, for cubics, we kind of said this. We said, okay, you're going to have 3 sets of 4 equations each. So you have 4 equations and 4 unknowns. Well, let's argue this way. If I give you some sort of conditions, I give you one condition. That's going to determine an equation where you have a value of p for that value of u. Say u equals 0, u equals a half or a third. And that's going to give me one equation. Well, if I have 4 equations and 4 unknowns, generally I can solve them, and for the kinds of curves we're going to talk about, we're always going to be able to solve them. So we're going to get 3 sets of 4 equations and 4 unknowns to solve, and each type of conditions is going to give us a different set of equations that we need to solve, and that's what we're going to be talking about in the next lecture. One other point I want to make here is that I probably should have made earlier, is that the range of u really doesn't matter. We're going to always make it over 0 to 1, but you can always scale it to be over any other range, because it's just a linear transformation to make u go, instead of 0 to 1, from some minimum value to some maximum value. So I'm really not going to lose anything here by saying u can only go between 0 and 1. Now, finally, for this lecture, A surface is just go to a form that has a second parameter v, and if a polynomial cubic polynomial surface, or it's called a bicubic because it's cubic both in u and v, has all the possible terms for u to powers 0, 1, 2, and 3. So you have 4 possibilities for u, for powers of u, 4 for v, so you sort of have 16 possibilities here. So that says you have, for each of x, y, and z, you're going to have 16 equations, 16 unknowns for some set of conditions that we're going to talk about next time, and they're independent of each other. So you have 48 coefficients here because this is an equation in x, y, and z, but I'll be able to deal with x, y, and z separately. And what I'll tend to do in the next couple of lectures is say P is a scalar, not a three-dimensional entity as it is here, and it's a three-dimensional, it's a one-dimensional entity where P could be either U or V, or either X or Y or Z, because I do exactly the same thing for X, Y, and Z. So it just avoids me having to write things down over and over again for X, Y, and Z. So in other words, each of these terms in here is of this form where P, this is just a scalar equation in which has polynomial values of U and V going from power 0 to power 3.